I am glad to be here at Strange Loop. My name is Jamie Jennings. I recently finished a short 19-year career at IBM. In the time between submitting this talk a few months ago and now, I have moved from IBM to NC State, where I am now once again a professor of computer science. And Rosie has moved from GitHub to GitLab. We are both happy in our new digs. So I'm going to tell you a story about a domain-specific language, and I hope that some people will take away a meta-level message, which is sometimes creating a domain-specific language is a really good way to solve a class of problems. And so this story began while I was at IBM, and my team had to write lots of regular expressions, and we found a number of things that we did not anticipate about what happens when you have a large collection of regular expressions used by a large collection of people writing in different programming languages, Python, Perl, Scala, Java, et cetera, even a little bit of C and C++. And also, when the data sizes increased, we found interesting performance anomalies that kind of panicked us briefly, but we went on, and I designed Rosie Pattern Language as a way of solving some of the issues that we had with regular expressions. So, by the way, I'm used to teaching, and so I usually walk around and actually physically point at the screen, which I can't do here without risk of falling off the stage. So, yeah, I could walk around behind the screen, but that looks weird. Okay, so I may walk around a little bit, but I know for the camera I should try to keep still. Sorry. This was the situation at IBM when I was working on Rosie initially. We had, within IBM Cloud, a set of DevOps tools, and they include several hundred tool integrations. A few of the popular ones are shown at the bottom, and they include source code repositories and issue tracking systems and requirements management systems and unit tests and build systems and deployment systems. And what we were trying to do in my group is take all of the digital exhaust, if you've heard that term, all of the metadata and logging data that is spewed off by these systems as they run, and see if we could come up with useful insights to give back to the development teams about their projects. So we were trying to measure things like how agile is your project, how did changes in your project's management affect your ability to respond to issues quickly, how much effort are you spending on issues versus bugs, and in fact we could even do a reasonably good prediction of which changes to which files are more likely to have bugs in certain commits. And so we did all this by combing through data that includes some natural language, some structured data, and some semi-structured data. And what we found was that we thought we had a big problem because there was a lot of data in a lot of formats. Planet-wide, the problem is much, much bigger. We produce roughly 2.5 exabytes of data a year, and this estimate was made several years ago, so it's surely gone up. Best estimates are that very little of that data is actually ever analyzed, and so this means that there is the potential to gain insights from a lot of data that is never actually looked at. And if you ask a data scientist why we aren't looking at more of the data, they will probably draw you a flowchart similar to the one on the right, where they say, look, from the day that you give me a new data set to the time when I can actually do some analysis, are all these steps in between where I have to write some code or some expressions for parsing the data, and I've got to make sure I do that correctly, and I've got to do some semantic annotation and maybe some other things. And Rosie Pattern Language was designed to address those first few steps. Okay, so we did what everybody did when we were faced with unstructured and semi-structured data. We reached for regular expressions, and you will know that these are tools that have been around for a long time. The concept of regular languages goes back a little bit further, but as a practical tool for technologists to use, it became popular in the 70s, and particularly with Unix and particularly on the command line. And this is an interesting point of origin, because the usefulness on the command line and while editing, I think, led directly to how concise regular expressions are, which is great if you need to be concise. If you don't need to be concise, it means that the syntax is fairly cryptic. Now, fast forward to 2017, here are 20 or 25 of the most common regular expression syntaxes. They are mostly incompatible with each other, sometimes in obvious ways, like some supporting features that others don't, sometimes in very subtle ways that you don't find out until the 3rd or 4th terabyte of data has gone through your system and you're not getting out what you think. Okay, so how many people have written regular expressions before? Yes, okay. So you can all read that top one and see, yeah, that would match a date. Yeah, no problem. But if you were given the bottom one, like, would you know that that matched an email address? You can probably figure it out faster than I could. I find this stuff amazing that people write regular expressions that have hundreds, if not thousands, of characters. So the first thing we observed was that if we're going to have a domain-specific language, we have to be able to name these things. And there's several reasons for that, one of which is we can't keep going to Stack Overflow to find regular expressions. Okay? And there's a great example that I sometimes show when I have longer time for a talk, of a regular expression that is probably twice as long as that email example, and it's for matching IPv6 addresses. And there's a lot of comments on Stack Overflow thanking the person for posting this. And then about 75 comments down, someone wrote, there's a bug. So one of the reasons that we we had to name them was not just reuse, but so that we could put them into libraries. And then when there's a bug, we could actually fix it in the library and everyone would get the update. And so the libraries have namespaces, like in this case, the net library, or up at the top, the date library. And each package namespace then has a number of patterns defined within it. So I'm going to kind of speed through, since you're a very experienced regular expression audience, I'm going to kind of speed through these 3 issues. Regular expressions are notoriously hard to read and maintain. Oh, has anybody ever gone and Googled for a regular expression help application? Yes, okay. So this was another issue. You go to the web in order to debug something that came up while you were writing a Java program or a Scala program or something. Okay, so what did we do with Rosie and Rosie Pattern Language to make an improvement on this? We designed a syntax that looks like a programming language. So patterns can be named, you can have whitespace and comments, and I realize you can do this in some regular expression languages, unfortunately not all of them. So when my team was trying to share sets of expressions between different programmers, we had difficulty with that. The expressions in the Rosie Pattern Language also compose. And this is critical because regular expressions do not compose easily. You have to be really careful. So we wanted to be able to build a set of small expressions and then build up from there to more sophisticated libraries. Okay, this may be a surprise. It was certainly a surprise to us, but regular expression performance is highly variable. So this slide and the next are the good, the bad, and the ugly, which you know if you speak Italian. So regular expression matching can be very efficient, right? Like we know from college or the kind of reading we do for fun if we're real super geeky, like I am, that linear time matching, right, using non-deterministic finite state automata is possible. Linear time in the size of the input. But almost nobody implements it that way. So what happens in practice is exponential time backtracking is the most commonly implemented algorithm, and it's used almost everywhere. Fortunately, if you're really good at writing your regular expressions, you won't end up in a situation where your program suddenly takes exponential time. But it does happen. So here's an example of a 90-something character input. and the input is comma-separated values. It is one line from a CSV file. And yet, if you're trying to find out if the 29th field was a gold medal, this takes 65 seconds to run in Perl when it should take fewer than that microseconds to run. So this kind of exponential backtracking, in a lot of small programming domains, you won't ever trigger it. But in a large domain where you have a lot of patterns written by a lot of people, and there is a wide variety of data flowing through at high velocity, you will eventually hit this, and then your big data pipeline is stalled. So what did we do? RPL is based on parsing expression grammars, which I'll talk just very briefly about, but they are defined as, formally, like regular expressions are defined, but they are strictly greedy and possessive, which means that backtracking is really limited in the sense that you have to control when you write your pattern how much backtracking you're willing to tolerate. So it makes it difficult to be accidentally inefficient. We also, in the cloud division of IBM, we make a lot of use of the ELK stack, Elasticsearch, Logstash, and Kibana, which has been great for us for log processing. And so we looked at Logstash and we said, well, Logstash uses Grok, which is a library on top of regular expressions that lets you create lists of regular expressions that you can reuse. So maybe we should use that. And we found Logstash, and Grok in particular, ships with 120 common patterns, and you can add your own. So why not stop there? Well, the caveats we found were there aren't any real packages, so there are possible name collisions. And some implementations we saw of Grok, as you load in different batches of patterns from files in a directory, some of them will use the first instance of a defined name, some will use the last. So there's a lot of irregularity there. And of course, they're still regular expressions, so they still look like this, right? And here's a diff. So how many people can spot the error, the difference in quoted string from the top to the bottom? Well, actually, quoted string is the easy one, sorry. It's IPv6. So there's a difference between those two entries, and Lord knows exactly where it is. So sticking with regular expressions seemed like a bad idea. So we designed Rosie Pattern Language to read like code so that it would also then diff like code and be maintainable and debuggable like code. We okay? Yeah? Okay. Okay. So I've said all this without actually telling you what it looks like. So let's take a look. Okay. Here is a Rosie Pattern Language file that defines JSON in, I don't know, about a dozen lines. And it can only do that by making use of the definition of string and number and word that were already defined. There is a recursive grammar in there. You'll see a grammar section bounded by grammar and end. And this is a feature of parsing expression grammars that is something that regular expressions cannot do. So one of the things we observed while considering different regex libraries is that a lot of them have extensions that let you do things that are technically not regular anymore, regular expressions. And one of those things is matching recursively defined structures. So JSON, HTML, XML, things like that. And so parsing expression grammars can do everything regular expressions can do, plus recognize recursive data structures. So what you'll see in this file are the things you'd expect to see in a source code file. Comments, there are references to modules. You don't need to import anything or declare a package unless you want to, so it's easy to write just a few lines of RPL that don't have any boilerplate. There are identifiers, like you can see true, false, and null are identifiers defined to match literal strings, true, false, and null. The literal strings are in quotes, which separates them from what in regex are known as magic characters. There's a lot less magic here. So literals are in quotes and identifiers are outside of quotes. I'm not going to talk you through the grammar, but it's fairly trivial. Unit tests are an important thing to note. I haven't seen a regular expression library yet that lets you declare executable unit tests. And for us, that was really important because when we are calling Rosie pattern matching functions from Python or from Java or from Go or from C, we want to know that at runtime, in production, those patterns are going to work and not have typos or bugs or other bugs. And so at build time, one of our build steps is to run the unit tests, which is something that Rosie supports. And I'll come back to that. OK. So let's look at a few features before we kind of look at some more use cases. So I posted a series of tweets which were a little bit obnoxious because they were called, "Can your grep do this?" Luckily, I didn't hear back from any of the ex-Bell Labs people. But the first thing is named patterns. So here's a curl command that pulls down what Google's homepage looked like last night. And if we wanted to extract from that, from this big mess of text, all of the URLs, what would we do? We'd probably pipe it to grep. And in this case, if the slide will advance, there we go. In this case, we're going to pipe it to Rosie, and Rosie has a grep command, which more or less emulates grep. And I originally implemented this just for command line demonstrations, and it turned out at IBM to be one of the more frequently used features, was just the command line. So if I grep for net.url common, what I get out is literally this output. Now, I could have said Rosie grep net.url, but net.url was written to match exactly what the RFC says is a valid URL, which includes all words, single characters, bizarre combinations of single characters and numbers and dashes. So we wrote URL common to just take the common kinds of URLs. So this is a really useful thing. You'll notice in the command invocation, there's a -o subs. -o controls what kind of output do you want. And in this case, it's the sub matches, which is kind of a technical thing that's not important here. Okay. Here was another, can your grep do this? At the top, I pull out lines 46 to 49 of the system log file on my machine, and then I pipe that. Second command is take that same set of lines, pipe it into Rosie with the match command. And here, the pattern I'm matching is called all.things. All is a package that just has a collection of collections of things. And all.things is a disjunction of, I don't know, maybe 90 or 100 different kinds of things that we might recognize. It's not especially fast, this particular pattern, but when combined with syntax highlighting, which is built in, you can get output that shows, for instance, path names in green and network names of different kinds in red, timestamps in blue, numbers of other kinds are underlined, and random words are in yellow. And you can, of course, customize that mapping. And when you write your own patterns, you can assign them colors so that as you work at the command line, you can recognize things easily in the output. And this is because one of the other things that really killed me about regular expressions, my teammates were rather blasé about this, but I didn't like the fact that all of the tooling simply output plain text. In other words, it gave me as a human being very little to go on in terms of recognizing whether or not it worked, or recognizing whether or not I found the thing that I was looking for. So this kind of syntax highlighting turned out to be useful. It's also the kind of demonstration that managers understand, which helps keep your project funded. Showing things in color it's nice. OK. And they can show that to VPs, and they say, wow, that's great, color. OK, so So this is the kind of output I was generating with Rosie before I did the color output. Because Rosie is capable of parsing, of using a grammar and parsing input that way, which is something regular expressions can't do, you do get out a parse tree. And a lot of times you're not interested in the nesting of the different components, but if you were, you could see that num.denoted hex, a denoted hex number in Rosie is something that starts with 0x, and a hex number does not have to start with 0x, but every denoted hex number has a hex number inside, which is with the 0x removed. So you can see the substructure, and if you were then taking this data and piping it into another program for analysis, that other program could then extract just the pieces of the match that it was interested in. Okay. There is a formal basis for Rosie. I mentioned parsing expression grammars earlier. So the Chomsky hierarchy, came around in 1960s roughly. And you may remember that the strict definition of regular expressions is that they recognize all the regular languages. Well, parsing expression grammars came about much later, early 2000s. And as someone who is very fond of computer science theory, I am so happy that people are still working in this area and producing new and useful things. So when I saw parsing expression grammars, I said, this is great. This is a principled way to extend regular expressions, to not lose any power, but to also recognize context-free languages and some context-sensitive languages. There are a bunch of really interesting papers. By the way, there is an open question as to whether or not all context-free languages are recognized. I can tell you more about that than you want to know if you ever want to talk about it later. Okay. So I wanted to mention some syntactic and semantic similarities. So RPL and regular expressions both have repetition. In RPL, repetition is always greedy and possessive, but we use the same syntax as in regular expressions because other than the fact that it's a possessive flavor of repetition, the concept is the same. We have also character sets. And again, we adopted the same syntax as regular expressions because the concept is the same. We did do a little bit of simplification. We looked at the common errors that people make while constructing character sets, and we decided right away that you should be able to write a character set that is a list of characters to match, or a range of characters to match, or a named character set, but you shouldn't be able to just mix and mingle and drop them all together into a single set of square brackets, because that makes it hard for people to parse. If it's hard for people to parse, then they don't understand what your intention was, and maintaining it is difficult. And then, of course, we have operations like look ahead and look behind and negation, and these are simplified syntax from regular expressions. Okay, there are many differences between RPL and regex in syntax. One of them is very important. Parsing expression grammars are defined with a choice operator that uses a /, specifically because we want to visually distinguish it from the vertical bar in regular expressions. So the vertical bar is unordered alternation. So you get choice A or choice B, and you don't know or care which order those are going to be tested, and it's not possessive in regex. So if one fails, you will go back and try the other one. And if one succeeds, but then later the match fails, you'll go back and try the other one. In parsing expression grammars, the choice is ordered. It always tries P first and then Q. This is a place where a compiler, like the Rosie compiler, can be smart about ordering your choices or giving you hints about choices that are not in a good order. So that is a part of ongoing work. But it's a slightly different concept. I think I know what's going on. I'll just avoid hitting the podium. Sorry. Okay. We do ship a standard library with Rosie, which used to contain everything on this slide pre-1.0. When I released 1.0, I took the stuff in green, source code destructuring and syslog type patterns, moved them over to a community repository, mainly because those are things that will probably change and the collections will grow over time. It's unlikely, for instance, that some of the other ones, like the definition of IPv4 and IPv6, are not going to change. And so we can write those once and simply maintain them when bugs are found. But there's a variety of commonly used patterns there. Okay. I asked you about debugging earlier because if you search regex help on Google, it gives you roughly 8.5 million options for pages you might visit. So clearly, debugging regular expressions is an issue. We wanted to have better tooling around debugging for Rosie than we were forced to use when we were using regex. So here is a command at the top of the screen that says echo something that looks like a time into Rosie and try to match RFC 3339 time format, which is a very common time format. And it doesn't match. So you get back no output, just a prompt. And so you may wonder, why didn't it match? And you may ask, what is behind the curtain? Behind the curtain is the output when you replace the match command with trace. So if you say trace instead of match, you get out an entire hierarchical trace, which looks and functions very much like a stack trace. And you don't need to learn to read this here. Just like with stack traces, you will, with a little bit of experience, learn to look to see exactly what's going on. And it turns out that the failure point is down there near at the bottom. But the key value is that every step of the attempted match is shown. And at every step, you get to see what is the matcher looking at in the input and what sub-pattern are we trying to match at this very point. Okay. I have to speed up a little bit. Okay. There is a read eval print loop. I spent, I don't know, 25, 30 years maybe hacking Scheme and Lisp. And so I am used to working at a REPL, and I think it's a great way to develop. So I wrote one for Rosie. Inside the read eval print loop, you can type in Rosie Pattern Language statements like import, and then you have a number of commands that are outside of the language that are commands telling the interpreter to do something. And so here is .list. So you can .list the contents of the package that you just imported. And there is .match, so you can say, I want to try matching the destructure package .tryall is the name of a pattern which tries a number of destructuring operations. And here's some input that has a bunch of numbers. They're semicolon separated. They happen to be in parentheses. The tryall method looks for sequences of things with common separators in between and ignores and strips off the parentheses, brackets, braces, whatever. And so what you see is there are some snip marks here where I left out extraneous input for the slide, but it pulls out the data 1.2, 3, 4, 5, 6, and 7. And the pattern definition did not know that the input was going to look like that. It just tried a number of things. So we're using this in a data science package called Pixie Dust from IBM. Okay, I already mentioned executable tests. So you can write your test cases, which are great ways of documenting what your expressions are supposed to do. And you can run them. And you can run them. Hello? Okay. Okay, it's not showing you the output from running them. Sorry. Trust me. You can run them, and then when some of them fail, you get details as to why they fail. Okay. So I want to mention a few non-CLI use cases, because all the examples I was showing you were at the command line, and then we'll finish up. Okay. The first non-CLI use case is the one I started with. So I built Rosie at IBM because we had this big data pipeline. We have a cloud. The cloud has a bunch of DevOps tooling. The DevOps tooling has a plug-in sort of architecture, and there are integrations for around 200 different tools. When our customers are using our cloud and these tools, we can, if the customer wants this, we can analyze commits and commit messages and issues and responses and test outputs and builds and deployments and things like this. We can even look at log files from the running application. So all the way from dev along to ops. And we can try to produce insights on this data. And so what we did architecturally was basically the pattern you see here. All of the raw data comes in, gets run through Rosie to look for the pieces of the input that are of interest to our machine learning algorithm. So it is the first pass in feature extraction. And then it goes into storage where we do a number of things on the data. Another application that is quite interesting to me personally is parsing source code. And if any of you saw Max's talk on Tree Sitter earlier today, there's some good overlap between what his system does and what Rosie does. Even though they were developed really differently for really different purposes, they're both good ways of parsing source code in multiple languages. And in order to kind of demonstrate the breadth, I asked a group of students at NC State in North Carolina to write RPL patterns to extract as many features as possible from 10 commonly used languages, including Bash, because a surprising number of service outages are due to errors in scripts. Big surprise. In any case, this is a little bit work in progress. They're still finishing out function bodies and class bodies, but they can pull out things like literal strings, comments, imports, where exceptions are thrown, a number of different calls to logging. So you can imagine that without having to have a parser for a particular language, you could do a lot by not. So when you want to parse source code and you don't have a parser for the language, it's still possible to pull out just the pieces of the source code that you're interested in. And if you can do this in a principled way, you will get out things like actual statements and not statements that are commented out, right? Unless that's what you're looking for, in which case you can do that as well. And then last, secure engineering principle. So I did it again. Okay. For people at home watching the video, I'm sorry. Oh, is that what it is? Ha! Thank you. Okay. So the open web application, okay, now I'm doing something different. The open web application security project has been putting out reports for, what, more than 10 years? Yeah, since 2003, 15 years now. And every single report says injection attacks are the most common form of attacks against web applications. So what do they recommend? What does everybody recommend? Whitelist all the input. What does that mean? You have to parse every piece of input that your application sees. So what would you do? You would use regular expressions because that's what everybody does. But that's what I'm trying to change. There should be a better way, something more principled perhaps, something where there's a library of shareable patterns and we can maintain that library over time as we learn about new attacks. Okay. I'm going to finish up with how Rosie is actually used, not at the command line. So if you're programming, for instance, in Python, you do the same things that you would do using a regular expression library. You get an engine or a matcher, you instantiate that. Some packages just instantiate one, and so they do it implicitly when you load the package, but Rosie lets you have as many pattern matching engines as you want, which is great if you're using threads. But of course, if you're using threads, you wouldn't be programming in Python, so it's better used in Go. Okay. So you get an engine, you compile some RPL, and compilation could be a string that you assemble on the fly, like in this example, or compilation could be done on a single symbol, and that symbol would be something from one of the libraries. And then you do the matching. There are some weird Python things around strings, Unicode strings versus byte arrays. The Rosie library right now is not very Pythonic, which I understand to mean embraces the idiosyncrasies and hazards in the Python language. We're working on making it more Pythonic. If anybody wants to help, that'd be great. So today we support C and Python and Go. In the past, before 1.0, I supported Node and Ruby and Java and Lua and was aiming at Clojure because that's my... I'm so thankful that there is a place for a Lisp programmer to go in 2018. Okay. So I'm going to update those libraries at some point or get some students or some volunteers to help me because I get requests for these languages all the time. I should mention performance. Performance is really good. It's hard to find comparable packages that do similar kinds of work. We compared to Grok because we use it a lot at IBM, and Rosie is roughly 5 times faster on the same problem, extracting the same artifacts from the same data. I will note one thing on our tests. Grok, whether it was running in Ruby or JRuby, dumped core when it found a UTF-8 decoding error. This is not great behavior. In production, it doesn't completely stop. It just drops that line. It never parses that line, goes on to the next one. This shouldn't happen, right? This is a bad thing. So anyway, we're happy with 5 times faster, and we've done literally no optimizations. Oh, and Rosie is running single-threaded here, unlike JGrok, which after the JVM startup time, apologies to all the JVM language users, including Clojure, after the JVM startup time, it works very well. Okay, but not as good as Rosie. So here I'm going to wrap up. This is attributed as African proverb, but nobody can trace it back to any actual place. So it's a wonderful saying, but I just call it proverb. So here is our roadmap, which looks kind of empty. Let me fill it in. Okay. So I'll tell you about 1 or 2 of these. BottomRight, ahead of time compilation. Right now, when you fire up Rosie, it takes, some hundreds of microseconds maybe, or a few milliseconds to compile all the patterns you're going to need. We could eliminate that startup time by compiling them ahead of time and saving them to disk. Top right, extensibility. We have the ability to write macros in Rosie, which are great because just like in programming languages, they let you take syntactic structures that you want to repeat with some substitution and write them as a macro, so there's less repetition. Having user-written macros is difficult because right now you have to program in Lua and you have to know enough about the internals of Rosie. So we're working on a macro implementation language that is more accessible. And there are lots of other interesting things going on. So I will finish up here with a call to join us. If you want to try out Rosie, just do git clone of our GitLab repo and type make, and then you will have a local directory bin, which has bin Rosie, that you can try things out. If you are interested in contributing patterns or writing tools that help people write and debug their RPL, that's great. We're always interested in new features, including features that help with performance, features that help with writing succinct patterns instead of longer ones. So there's a lot of work going on in those areas. So now I'm going to switch over to Slido and take a couple of questions. Thank you. Okay, the one at the top. Oh yeah, how does Rosie interface to other programming languages? Rosie's implemented as a C library, shared object, and so you can load it dynamically into things like Python and Ruby and JavaScript, or it also compiles as a static library, which is great for languages like Go. Okay, given a Rosie pattern, does Rosie have a command to generate regex with identical semantics? Oh, this is really interesting. No, but we're actually working on the inverse problem. So that will probably give us some insight into this particular problem. I've got a student who wrote a regex to RPL converter. So that's a great start. Unfortunately, it's limited right now because it only looks at the proper, strict definition of what a regular expression is. So if you're using Perl-compatible regular expressions and you want to put in, \s for whitespace or \k for whatever that does, it won't recognize those. But we would like to take this and make it possible for you to take regex that you already use and simply import them and use them as RPL. I never thought about going the other way, but if you're interested in elaborating on why, please let me know. Okay, we'll do one more. Given a Rosie pattern, can you dynamically generate a string for which it will match? We don't have that built in, but I think this is a great use of formal languages. So once you have a Rosie grammar, right, it could be not a recursive grammar. It could be just a straight linear thing, a set of definitions. You could use this as a generative grammar. And you could use this as the input to a fuzz tester, which would generate strings that match the grammar, so that you could then feed those into a program or a system, an application, that perhaps uses Rosie as its parser, and so you know it will accept those strings, and you can now then test to see the behavior of your application once you know you're passing the input. And so, yes, I'm very interested in that topic. And last one, support logical rules as part of the match. We don't have plans in that area yet, but it's clearly an interesting topic. I'm a little bit wary of stepping outside of the formalism that we're using now of parsing expression grammars, only because the history of regular expression expansion tells us that that when you add things in an ad hoc way, you can sometimes get really bizarre results, and I do want to avoid that, but the idea is really interesting. So thank you again.